Back with a nice integral that I saw on the site integrationb.at from Austria. Nice one. Integrating from 0 to 1, arc sine squared x over square root 1 minus x. Something that really pops out at me. I know for a fact, all right, let's get back to this. I know for a fact that the derivative of the arc sine function, remember that's the inverse sine, the derivative of the arc sine is 1 over square root 1 minus x squared. And that almost looks like what we have, except we have a square root x in there. So it would be nice if that square root x in the arc sine was gone. So we're going to go ahead and make a priming substitution here. Let's do that here. Let's set y equal to square root of x. Or rather, we're going to set y squared equals x. So that's 2y dy is equal to dx. And because of our interval, it's really nice, 0 to 1. We don't really have to change the interval of integration because, square root of 0 is 0, square root of 1 is 1. So let's go ahead and toss everything in. Integral from 0 to 1 of 2y arc sine of y now, because we have x is y squared, and the square root of y squared is y. And then we have the denominator, a square root of 1 minus y squared dy. And this pops out to me very nicely because now I can use integration by parts. I'm not going to go ahead and write the full thing because you should know it. But I'm going to write this integral in a nice, clever way here so that we can get a feel for what our u and dv are. We have 2y. And now I'm going to have d of arc sine y squared. Okay? So that's almost what we need, except when I take the derivative of arc sine of y squared, that 2 is going to come out. So I need to absorb 2 outside the integrand there. So now I have y d arc sine y squared. And now we just apply our usual integration by parts formula. So we'll have, so for those of you that can't see it, we're going to set u equal to y and dv equal to, let's see what it is. It is going to be arc sine of y over square root of 1 minus y squared. And I'll keep the 2 in there. So that's 2 dy. Okay. So now that we have that, okay, we're going to go ahead and use the integration by parts formula. So y times arc sine of y, and that's all squared. Evaluate that on the boundary. And then we'll have, let's move this over. Move this up here. So what will we have left over? So y times the square of arc sine y, and it's going to be minus, okay, we're going to have minus the integral from 0 to 1 of arc sine of y squared dy. Okay, now the cool thing is this first integral is pretty easy. Okay, at 0, we have arc sine of 0, which is 0. And of course, 0 times anything is 0. At 1, well, we'll have, let's see, let's just write it down. We'll have 1 times the arc sine of 1 squared. There. And then we have this one here, which we'll handle in a second. Arc sine of y squared dy. All right, now arc sine of 1, the angle whose sine is 1. If we think about our unit circle things, we're going to have a pi over 2. So then this is going to be pi squared over 4. Then minus, well, how are we going to handle the second integral? Well, the second integral we'll handle with another priming substitution to get rid of the arc sine y and decide the square. Otherwise, it's just going to be more integration by parts. The priming substitution we'll make here is we'll set y equals sine of t. So dy is cosine of t. So how does that change our integral? Well, we're going to integrate still starting at 0. Well, we may as well just write it out here. Okay, so we need t equals arc sine y. T equals arc sine y. So the arc sine of 0 is 0, and the arc sine of 1, as we said, is pi over 2. Okay, so now we will have, so arc sine of t is just t, so we'll have t squared. And then we have a cosine of t dt. And this is more integration by parts. Let's just go ahead and use the DI method here. Okay, so we're going to build our chart here. D, I. We'll choose D to be the thing that vanishes eventually, and when we take derivatives, that'll be t squared. So we'll take our derivatives until it vanishes. Then we take as many antiderivatives of cosine t. So then we'll have cosine, sine, minus cosine, minus sine. And then tic-tac-toe, plus, minus, plus. And we have everything we need. We'll have pi squared over 4 minus all of this stuff, okay, t squared sine of t, minus a minus, so that's going to be a plus 2t cosine of t, and then we'll have minus 2 sine of t. We're going to evaluate this on the boundary, pi over 2, 0. Now, if you think about this pretty cleverly, remember that sine of 0 is 0, cosine of 0 is 1, but sine of pi over 2 is 1, and cosine of pi over 2 is 0. Now, the fun thing is we have a bunch of 0 terms here. Okay, I will leave that as an exercise for you to see, but then on the outside, we'll have pi squared minus 4, pi squared over 4. And then we'll subtract. Well, let's just write it out. Pi squared over 4, sine of pi over 2, plus we'll have a pi cosine of pi over 2 minus 2 sine of pi over 2. Okay, and then when we have our 0 terms, well, we have a t squared, plug in 0 there, we get a 0. 2t, we plug in a 0, we get 0. Sine of 0 is 0, so this is all that we have to worry about. Now, what's the finishing move here? Well, cosine of pi over 2 is 0, so that's going to go away. Sine of pi over 2 is 1. Okay, so this whole thing is just going to be a minus 2. And so what's left over? We get a pi squared over 4 minus a pi squared over 4. Okay, that second term goes away, and then we have minus minus 2, which is plus 2. And the cool thing is, those first terms, they drop. And so our fun integral is equal to 2.